Let me get rid of that. So it's my great pleasure to introduce another friend and colleague, Professor Karl Bohringer of the University of Washington. He's a professor of electrical and computer engineering and bioengineering, and he's also the director of the Institute for Nano-Engineered Systems. Among his many awards, he's an Amazon Catalyst Fellow and an IEEE Fellow. You're going to see that his research focuses on surface control, including self-assembly and self-cleaning structures. It's my great pleasure to introduce Professor Karl Bohringer. The world stage is yours.
Oh, thanks very much for the introduction. And again, thanks very much to the entire team, including Alice and all our colleagues for putting together this great panel and this seminar series. So I think I will share my screen here. Let me just get this started. And you can let me know if you can see my presentation. Let's see.
Yes, just need to go into presentation.
And I think now it should be in the presentation mode.
Perfect. Yes.
Great. We've already seen a great talk this morning, and I think it will be very difficult for me to match the presentation by Jillian, but I also want to talk about some magic on surfaces. And in particular, we've been studying what to do with drops on surfaces that are microstructured. And but before I get started, just a few words of where I'm coming from. And sometimes people get a little bit confused about Washington. So there are many Washingtons, of course, in North America, but we are at the West Coast and in the upper northwest corner in the beautiful state of Washington and in the city of Seattle. We have a new institute for nano-engineered systems where we work on, for example, quantum computing, sensing, communication. We work on portable and wearable and implantable devices, and also on techniques to scale up manufacturing at the small scale. As part of the Institute, we have one of the largest clean rooms in the Pacific Northwest. We would just mention it in the panel earlier this morning about the students working in there, and really all of my group members spend a lot of time in that clean room. And then we're also part of a larger network across the United States. It's called the National Nanotechnology Coordinated Infrastructure. This is supported by the US National Science Foundation, and it really brings together a lot of the schools that work in nanotechnology and related topics in the United States. So it's a great network where people meet and exchange ideas and also talk about problems and challenges and how to just do better science and better engineering. Here's an outline of what I want to talk about today, and there are really roughly 3 different sections. First, I want to give a more general introduction on making a point that often it's difficult when you scale down things. You have to work with more limited capabilities of manufacturing. You have more limited abilities to build sensors and actuators and other kinds of components. But sometimes you can also take advantage of that and actually simplify your devices. Then I want to talk in particular about some fundamentals of the interaction between liquids and solids at the small scale and about droplet microfluidics. After that, I want to switch into a more applied field in self-cleaning surfaces. And this is actually work that was primarily done by my student D. Sun. He just graduated. He's still here in the Seattle area, but now on the other side of the lake at Microsoft and working on the HoloLens project. He also just published his latest papers in the Nature Springer Microsystems and Nano-Engineering journal. So you'll see some brand new work, but you'll also see maybe how old I am, because I'll show some work that goes back a couple of decades. So hopefully we'll see a nice span of different research projects across really the many years. So that's the rough plan here for the presentation. So hopefully this is interesting for everybody. And so let me just talk a little bit more about the motivation, also what gets me excited about this work. So of course, microsystems are exciting in itself as building things at a very small scale, and to explore, well, what kind of capabilities are there? What kind of effects can you take advantage of at the small scale that maybe are not available at the normal scales in which we live in day to day. So also just taking advantage, exploiting opportunities to find simpler solutions. And what I mean with that, I want to just show you a few examples, and I'll go into some of them in a little bit more detail in a few minutes. But in general, I want to look at interactions.
I'm not hearing you. Are others?
Sorry, was there a comment or a question? Okay, so I want to look at surface interactions at small scales, and for example, that when you work in robotics, then you can actually do a lot without sensor input if you know something about the world in which you're operating. Simplifying robotics by eliminating sensor input, self-assembly, where you're actually eliminating the position feedback, the pick and place operations, and just let the system settle in its natural state. We worked also on microfluidic devices, in particular something that we called microfluidic origami, where we don't really need any active components to move liquids, but just achieve that by folding structures. And what I really want to talk about today then is about droplet gradients, droplet ratchets, so some kinds of surfaces where you have more control of handling and manipulating small amounts of liquids. And again, ultimately, you can achieve that without any moving parts. So you build microfluidic systems that are very easy to build, also quite easy to operate, and still accomplish a lot of the functionality that you would expect from a more complex system. Let me go all the way back many years when we worked on micro robotics, and in particular in something that we called micro MEMS Cilia. So biologically inspired devices that are very simple. They just have a single degree of freedom and wiggle. But if you have many of them working in parallel, working in coordination, then you can actually accomplish things like moving a larger object on top of a surface with, say, hundreds of thousands of these actuators. So in this video that I hope you can see at the bottom, you've just seen how this small chip, this is about 3 millimeters in size, is being transported on one of these, well, what we call the smart surface, with hundreds of small micro actuators that can move an object, or maybe in this case, rotate it. And in particular, as I mentioned, you can also do some positioning without any sensor feedback, just by knowing where these actuators are pushing. So from the left, on the left side, these actuators push towards the right. On the right, they push towards the left. So the resulting effect is a force equilibrium that will always settle a larger object on top of the surface in the center. So you're essentially doing sensorless manipulation, moving an object to the center of the screen. And you're doing that, yeah, as I said, without any sensor feedback. Now, taking this idea a little bit further, first turning this upside down, I should say. So we're taking these chips with hundreds or, well, many hundreds of legs, and letting them point downward. Well, what do you get? You get a walking chip. And this was actually a great project that initially started at Stanford with my colleagues John Saw and Greg Kovacs, but then evolved into a little robotic project that actually was done by an undergraduate student in my lab, Matt Mohebi. And he put these chips together, wired them up, so you can maybe see in this picture there are some control wires coming in. As far as I know, this was the first walking micro robot with hundreds of legs that had full 3 degrees of freedom motion, so X, Y, lateral motion, and also rotation. How does this look like? Well, here is a little video, and you just see one corner of this robot, and you see a few of its legs, and here you can see how it's sort of crawling along the surface. It's a polished silicon surface, so you can see the reflection as well. And with these hundreds of legs that are moving in a coordinated fashion, the robot can move to the side. It can also move in the opposite direction and rotate and reposition itself. Now, I mentioned earlier that some of these micro manipulation tasks don't really need any sensor feedback, but I wanted to take this to one step beyond that and go to self-assembly. Now, I'm not a chemist at all. We saw some great work earlier in this session on self-assembly at the molecular scale. We're doing something a little bit more, well, should I say, crude, with silicon microchips that are usually in the size of hundreds of micrometers, possibly down to tens of micrometers. But you can create a template where slots represent essentially the minimum energy state. And then when a wave of parts is moving over that surface, then these parts get captured in these sites and then assemble into a predictable pattern. So in this case, we have about 200 sites that capture parts. And my student Ji Hu not only built the system where you do the self-assembly, but he also built a vision system that tracks every successful assembly. And you can see that in about 10 seconds, we have the entire surface filled. So all the slots are filled with the with the silicon chips. With this very simple setup, you can really get to speeds that are higher than even the best pick-and-place robots that are on the market right now. So we are essentially working at a scale where the conventional techniques may not work so well anymore if you think about conventional pick-and-place robotic operations, but we're exploiting techniques that we know about, the microscale or the nanoscale, where we take advantage of energy minimization and self-assembly to accomplish, you could say, quite complex tasks of assembling hundreds or thousands or even more components. So this was just a little review of some earlier work, but I think it created some of the motivation for the work today. But what I've shown you so far was work with solids and how they interact at the small scale. But for the rest of the presentation, I want to talk about the interaction between droplets and solids, so liquids and solids at the small scale. And probably many of you have seen pictures like this before. So the lotus effect, the lotus leaves, which have this amazing property that they repel water that, say, a raindrop that falls on it, and it creates this really almost perfect sphere of water that can roll off the leaf very easily. So we've been, like many other groups, we've been fascinated by this effect, and others before us have studied this in a lot of detail, and I think there is a very good understanding now what makes this work. Well, if you zoom in on the surface, then you see an almost fractal-like structure of roughness. You see features that are in the tens of micrometers or in the micrometers, and even the smaller scale that makes the surface very rough. And this roughness really enables the, super hydrophobic property of the surface that basically limits the amount of interaction between solid and liquid. So most droplet is really suspended in air, and only very few points make contact with this microscopically rough surface. So if you shake the leaf of the lotus leaf just slightly, then the drop starts to move, but it's somewhat unpredictable where it would move to. And maybe in nature that's okay, but of course for us, we would like to have more control over how we control how we move and manipulate the drops. So what we really would like to have is something like in this picture here. We have a platform where we can predictably move drops from one side to the other, like in this example for some biomedical or biochemical application, where the drop is moving from one side, picks up maybe some cells, then some nutrients, mixes them, observes the reaction, and when it's done, then it's getting disposed, and then maybe the next drop is coming in. And so how can we build something like this? And how can we exploit the particular properties of the small scale to make this very efficient? The most fundamental principle or task here is how to move drop from a point A to a point B. How would this work? Well, in general, you need some kind of gradients. You need some energy landscape that moves the drop from one position to another. So in this little animation, you're moving from the higher energy point to the lower energy point, following the gradient. Now, how can you do that in practice? Well, there are many different ways how you could create a gradient. And here are just some of the examples. And again, great work that in some cases really dates back many years. Like in this case from George Whiteside's group, almost 30 years ago, he showed that he can make drops move uphill. Now, why does that work? Well, because there is an energy gradient, or really a surface chemistry gradient, where the lower portion of the slope is more water repellent than the upper portion of the slope. And there is sort of a gradual change of the surface property in between. So if you put a drop on the surface at the lower end, then the overall energy balance gets minimized, even though you work against gravity, but still the water is moving uphill. There's some great work back then, Sandra Troyan at Princeton, who worked with thermal capillary effects to create some beautiful patterns here of moving mixtures of liquids in different directions. And then, of course, there's work from Duke and also from other schools on electrowetting. So applying a voltage that creates locally a different energy landscape that again moves the drop in a particular direction. Here is a side view in this video, and hopefully you could see that in a short sequence. Here is a top view, and you can also see how fast this drop can be moved around just by applying an electric field that attracts the water drop to a particular site. And in this case, there's an array of electrodes, about 10, 12 electrodes in the field of view here, and you can very quickly switch between them. And now, one more example, actually two examples on this slide, where the researchers took advantage of topography of a surface. The light and frost effect is well known to where you have a drop on a hot surface, and the local evaporation essentially lifts the drop and makes it move very easily. But now if you add some texture, if you add some asymmetry to the surface, then it turns out that there is a preferred direction in which these droplets move. So in this picture, you see there is some kind of ratchet pattern on the surface, and the interaction between that ratchet surface and the drop actually makes it move towards the right. Now, even in nature, so and you'll see in my presentation, I'll come back to that theme occasionally, because we can learn so much from what nature has evolved. So here is a bird that actually takes advantage of of a similar effect, where it has a drop in its long beak, and when it just changes the angle between the upper and the lower jaw of the lower part of the beak, then the droplet is actually moving towards its mouth. There's some beautiful work from David Kire's group together with Manu Prakash and other colleagues that showed that this is something that you can prove where a drop in this beak just by vibrating it, opening, closing it by a few degrees, will transport the drop in a particular direction, in this case from the left to right. We also got really excited about that and wanted to explore what can you do with texture at the small scale. So topography or structuring a surface. And now there are many students and postdocs who have worked on this over the years. We've explored different directions, and I will show you more about that today in the remainder of the talk, but here's just a quick preview. So the idea is that you have a structured surface with texture that may have more or less dense features in different regions. You put a drop of water or some other liquid possibly on top of that surface, and you observe what it is doing when it interacts with that gradient of texture. While I can also look ahead a little bit in our advanced materials paper quite a few years ago, we showed that we can make drops move on these rough surfaces, and we can make them move in particular in well-defined directions. So here's actually a stroboscopic image of 4 drops that are moving, and they get eventually merged and mixed at the center. And the amazing thing is that you can even do this upside down. So the roughness creates some sharp edges on the surface, and the water droplets essentially cling to these edges so they don't fall off, even though you could call this a hydrophobic surface. These are polymers that are in principle quite water repellent, but because of the roughness, the water drops cling to it. Here we put some dye in it to distinguish them better. When we just give them slight vibration, then they start moving, elongating, compressing, and with each cycle they're moving sideways along a track, and eventually in this case they mixed and merged again. And so what I think are quite fascinating effects with some very simple fabrication techniques, very simple principles, also with surfaces that can be built just in a few hours or less in a reasonably good lab. So I want to talk a little bit more in detail about how this really works. Then after that, we want to move on and look at some particular applications for that. All right, so now here's some science background, and I think this is one of the few slides that actually has some equations in them, but probably many of you have seen this already. So if you have a drop sitting on a surface, you call it the sessile drop, then it forms a certain contact angle. That angle is defined by the different surface energies. So the energies at the interface between liquid gas, at solid gas, and also solid liquid. And there's a very simple equation that relates this angle to these energies. So Young's equation, or sometimes called Young-Dupre's equation, gives you this relationship. And basically, if you see a configuration like this, where you have a relatively shallow angle or acute angle, you call this a hydrophilic surface, or the water wants to spread out. If you have a more spherical shape where the angle is larger than 9 degrees, then you call it hydrophobic. So the water actually is being repelled by the surface. And if you look at this diagram, well, it's really a simple vector addition. And you can also see that here, this is the way it's drawn here. It's really not an equilibrium because the vector components in the horizontal direction don't really add up. So in that sense, it's not quite right what's shown here, or at least it's not in equilibrium. But in the equilibrium, these horizontal components should add up to 0. Now, as I mentioned, we are really interested in not just flat surfaces, but also rough surfaces, because we saw, just for example, in the lotus leaf and also in other examples, that with roughness you can get some interesting effects. Now, as an engineer, first of all, I want to quantify. I want to describe what it really means when I talk about a rough surface. I want to talk about texture. How do I talk about that? Well, I give it some names. I give it some parameters. And here is one parameter. This parameter is phi. It looks at the relationship or the ratio between just the top of pillars and the overall area that one unit cell occupies. So imagine this is a surface where you have pillars sticking out, and the top of the pillars are, well, here colored red for just to distinguish it. And basically this parameter tells me something about the roughness of the surface, or maybe you could also call it the spikiness of the surface. How sharp are the pillars? If it's close to 0, it's like a bed of needles or a bed of nails. If it's 1, then it's a flat, smooth surface. So we're basically operating between 0 and 1, between for 1, a flat, smooth surface, for 0 or close to 0, a very spiky surface. Well, if it's just a little bit above 0. There's another parameter that also looks at the sidewalls of these pillars, but it actually turns out we don't really need that. So here it's important to remember the phi factor, because we need that later when I come back to my Young's equation or modified Young's equation. Here I'm looking at the apparent contact angle. So remember from Young's equation, we had an angle theta that we calculated from the surface energies. And now I'm asking, well, what happens when I put a drop on a rough surface? Here's the equation for that. But what does this equation actually mean? I think if you look at the graphics, it makes really perfect sense, because if you have a water drop sitting on top of a rough surface where the water does not sink into the gaps, then you have basically a mixture of water interacting with a solid and water, interacting with air. And what is the ratio between them? Well, it's really this factor phi that we were just talking about. So there is a portion of the water drop, and the surface area portion for that is phi, that interacts just like before with the flat surface. But then for everything else, for 1 minus phi, you have an interface to air. And when you have an interface to air, it's like this perfect hydrophobic area. It doesn't make contact with any solid surface. So there you have a contact angle of 180 degrees. So you can simplify that, and you get an angle that is expressed by this equation, or you can then turn it again into another, form. But what that basically means is that this apparent angle that you see is, first of all, different. Even though it's the same material, the surface energies haven't really changed here, except that, there's some air in the plane now. But what it means is that we're basically, now I went a little bit too fast, that the contact angle, this theta, becomes larger. So here you see that the phi basically reduces this expression here. That means the apparent contact angle is larger, and you get essentially a more hydrophobic behavior just by making the surface rough. Now, the colleagues Cassie and Baxter discovered this simple relationship in this equation. And again, this is many years ago. So this is not new, but now with our capabilities to build things at the small scale with very high definition, we can actually exploit this and build new kinds of systems that take advantage of this Cassie-Baxter effect. Now, I'll show you how this works if you zoom in a little bit more. So here's our Cassie-Baxter state, and I'm going to zoom in one particular area. And you see the interface here, solid liquid, and then also solid like liquid air. Now what happens if you try to push this water droplet if you try to push this water interface down into this gap? Well, we know that the material is already somewhat hydrophobic. So we have to apply some pressure. We have to exert some energy to push this water into this gap. So there's an energy barrier that naturally, if you let the system sit, it would not attain it. It would stay in the Cassie-Baxter state. But if you completely eliminate these interfaces, so the air-water interface and then also the air-solid interface, so you remove the air completely, then you get actually into a lower energy state. And another researcher named the state, or is named after this research. It's called the Wenzel state. Now, it's very difficult to get back because this is lower energy than the Cassie-Baxter state, but luckily there's this barrier in between. So what I would like to do is to stay on this side of the equation. That's what I will be showing you in the next couple of slides. So here are just some more pictures. This was done with a goniometer where we actually study the surface contact angles. And here you see the drop sitting on this bed of nails, while here we're pushing the drop into the rough surface, and here we have attained the Wenzel state. But both of these states, Cassie-Baxter and Wenzel, are both stable. And now, again, I want to take this a little bit further, and at this point, I'm actually I'm designing a rough surface. Now, what are the tools that I have available? So in my microfabrication facility, I can define these geometries, and I can create pillars that have a certain height. They have a certain geometry with a gap B and an actual size A. So if I look at this geometry, then I see, well, how does this relate to phi? Here's the equation for that. So a squared over a plus b squared gives me this parameter phi. And now remember the equation from Cassie-Baxter. So it tells me the parent contact angle is a function of phi. The theta is, of course, given by the materials. So I can play with phi here. And what happens if I change this from a flat surface to a very spiky surface? Well, I'm changing at the same time this parent contact angle from the original angle all the way to 180 degrees, at least in theory. In practice, of course, I have to stop a little bit before reaching zero. But this basically tells me a way to make a gradient of texture or a gradient of hydrophobicity on the surface. Now, if I know that, then I can fabricate it. I can create these gradients. And I take a wafer, I go into the lab. In this case, I create a lithography mask and a very gradual change in the size of these pillars here, not visible really in the SEM picture, but there is a slight gradient between the sizes. We made them in silicon in this particular case. You can also mold them in polymer. In this case, we coated the silicon with a Teflon layer to make it more hydrophobic. And then we can set up an experiment. So we can do a proof of principle. Here's my setup. Here's the gradient that I want to explore with a drop of water on it. I have a camera, and I need a little bit of vibration to agitate the surface to basically get the droplet out of the equilibrium state. And then I'm going to watch, well, what is going to happen when I give it this slight agitation? Does it have a bias to move from the or from the less hydrophobic state to the more, or from the less hydrophobic region to the more hydrophobic region? So here you can maybe see in the animation, I'm giving it some vibration with the function generator, and I'm going to observe that. Well, here's an experiment. So I give it vibration, and I'm going to observe this drop. And voila, I have the drop moving from left to right. Now, have I proven that this works? Well, maybe it seems like it, but as a good scientist, I should really do a control experiment, because maybe there's some bias here. Maybe I'm actually moving a drop downhill. So what I do instead is I'm building two different tracks two different gradients that move in opposite directions. And if the drops both move in the predicted direction, then I've essentially eliminated the bias in my experiment. So very important to be so honest to yourself and to your colleagues to do such a control experiment. And so in this case, there were two drops behind each other. And you can see that in this experiment, they're moving in opposite directions. It seems like this is working great. We have gradients. We have a way to make drops move on a surface just by texture. But unfortunately, well, they don't move very far. So we can ask, well, how useful is it really, what we've just built here? And this is definitely a limitation of these gradients. So you first of all have a limited distance along which you can move the drops. And of course, you cannot create anything like a closed loop because, well, that would be against the laws of physics if you want to follow a gradient. So what can we do to improve on that? We can build something like what we've seen earlier from my colleague Heiner Linke, who built this Leidenfrost ratchet. So we're building a texture ratchet. So we're building lots of small patterns that are like these gradients, but we arrange them in a clever way so that the drop moves from one gradient to the next one, and it doesn't move back. So we give it a bias so that the drop keeps moving along this, a repeated pattern of gradients, which then acts like a ratchet. Here's how it looks like, and this beautiful picture was done by my student Yegan Erdem, who's actually now a professor in Turkey, still working on microfluidic devices. So you can maybe see that some of the features are the same as what I've shown you before. So there's the roughness, the texture with lots of pillars, and there is another droplet here in the center where you have an asymmetric pattern on the surface. Now, how does this work? And here's a video with a high-speed camera, and I very much hope that you can all see that as smoothly as on my screen. But what you'll see here is the vibrating surface and the drop that's sitting on this track. And with each cycle, and we're going at about 50 Hertz, with each cycle, the drop is moving a little bit towards the right. And it's doing that just because of this ratchet pattern on the surface, because of the asymmetry that we are observing that we've created on this surface. So you can characterize that, you can study this in detail, and you can essentially see that the front and the back edge, so we call it the leading and the trailing edge of the drop, they basically have some kind of oscillating pattern, but with each oscillation, the drop essentially is taking a step forward. So the asymmetry on the surface is translated into a lateral force, into a lateral motion. And it's very predictable within a few cycles as we sort of increase the amplitude. The drop is reaching a steady state at which it's moving along, in this case, with about 12 millimeters per second. But you can actually do a lot more with this system, even though it's very simple. I mean, you can build this in a few hours, or maybe you can mold it in a few seconds, really, once you have a master mold. But you can, for example, build systems where different drops can be addressed with different frequencies. So it's well known that drops essentially have resonance frequencies, just like any spring mass damper system. And bigger drops have lower resonance frequencies than smaller drops. So if you use a low frequency, then you can reach drops that are, like in this case, 13 microliters in size or in volume. If you go to higher frequencies, then you can address and control drops that are maybe 5 microliters. And in this plot, we're characterizing the regions in which the drops are moving. So large drops at about 45 Hertz, the most efficient movement for small drops at about 80 Hertz. But if you have an intermediate drop, then there's some overlap. So there's a capability to address drops on a surface just by using different frequencies. And these pictures show some of these examples. So the first one shows just moving the 5 microliter drop towards the 8 microliter drop. And then we're changing the frequency and we're moving the mixed drop along that track. So first we do mixing and then some merging with the vibration. And when we change the frequency, we lower the frequency from 75 to 45 and the drops are moving together. You can do other kinds of experiments where different drops are moving. You can make them move towards each other. You can also use different liquids with different viscosities. So all of this is possible with this principle. Now you can also do things like, for example, what you could think of as some kind of microfluidic circuit where the drops initially move in an asynchronous way. So they're moving at different paths, they maybe arrive at different regions, but then you can modify these regions so that it's a little bit harder for them to move across them. And when you change the amplitude or you change the frequency, then you essentially synchronize the movement of the drops and let them all move on, like in this moment now, that they move together even though they arrived at this site at different times. So here's another example where you can essentially build a switch for drops. And again, it's the same drop, it's the same pattern on the surface, but in one case the drop turns towards the right, in one case it moves straight, because we're using different frequencies that essentially create different resonances in the drops. And for this higher frequency, the lower frequency, the drop is taking a right turn. So this was done by my student Hal Holmes. He had some great work on these microfluidic circuits that he's been building. And he's actually now still in Seattle, but working in a startup company and the overall theme of conservation biology. I think one more example on that, where you can have a selective mixing and merging of drops. So there is an area where drops are joining, but in some cases, like on the left, we're holding back the drop. We let the other one pass, but with a different input signal, we actually mix the two drops together. So lots of these functionalities are all capable on this platform. So very simple platform, only texture and nothing else. Lots of capabilities here and making interesting microfluidic devices. And I already shown this picture earlier, but maybe now it makes a little bit more sense. We have one of these, what we call anisotropic ratchet conveyors, these texture ratchets that drive the drops, like the upper left drop towards the right, the upper right one to the left. And we can even achieve that upside down because of the roughness of the surface. Okay, now you can even do things like droplet generation and splitting. So you have a larger puddle of liquid, and with the right kind of agitation, you can split off small drops. So that's also a very important function for generating individual drops in maybe a larger system. And you can maybe combine it with electrowetting as well. This was a nice project together with my colleagues Kumimura and Fujita in Japan, doing a visit there a couple of years ago. So you can make a drop, again, move along different paths. In this case, we have just one electrode system that essentially decides where the drop is moving, left, right, or straight. And now, these were the fundamentals that I wanted to show you, but now for the remainder of my presentation, I want to talk in more detail about one particular application, and I want to highlight my student Di-Sun. I mentioned his name earlier. He worked on this particular application of self-cleaning surfaces, and he was really great. He's been very productive, wrote a lot of papers that actually just came out over the last year, and was also very good at introducing different acronyms into the collection here. I've already talked about the anisotropic ratchet conveyors, or ARCs. He also worked on electrophoresis or dielectrophoresis, on electrowetting, on dielectrics, and on surface acoustic wave nebulization. So all of that was done on the same platform. and in particular, we're interested in exploiting this effect for self-cleaning surfaces. So let me show you what we want to accomplish here. If you look at solar panels, then ideally they would look like in this picture on the right. So they're nice and clean and the typical color for solar panels. But on the left side is a dirty array. So here in this picture, one half of the array was clean, the other one was not. And this is how it looks like if you're living in a sandy or dusty area, or maybe a smoky area, like we've been living here over the past month. Then you get some deposition on your panel, and that can reduce the efficiency substantially. So now there are different techniques how to clean that depending on how labor intensive and how water intensive it is, but a typical scenario is where you use about 1 liter per square meter to clean the surface. This is just one example. Here are some others. So of course in cars you also want to make sure that your lights are clean, or your cameras maybe in your self-driving cars, and there are some all sorts of solutions for that, but none of them seem particularly appealing, and a lot of them also seem to waste a lot of water. So what we would like to do is come up with a solution that's very efficient with water and also works essentially by itself without any human intervention. How can we do that? Well, first we looked at the literature, and there's some beautiful work out there. For example, the work by Joanna Eisenberg at Harvard that had these liquid infused porous surfaces that are extremely repellent to all sorts of contaminants, like in this little video where even some oil doesn't stick to it. So greenish areas are these slips surfaces, and you can see the comparison with a regular surface that is not treated, where the oil is sticking much more. Beautiful work also from C.J. Kim at UCLA on these super omniphobic surfaces that also exploit the texture, but to an even more extreme degree with these overhanging, so mushroom-shaped features. And then in general, with super hydrophobic surfaces, like here is a product that you can actually buy where a droplet is moving over a surface and essentially collecting the contaminants that are sitting on this wafer. The drop is basically moving in a random fashion, depending on the human that's controlling it. And then some beautiful work that just came out a few months ago of, again, some textures, some rough surfaces, but very durable ones. And that's really a topic that is very important, especially when you talk about solar panels that are exposed to the elements often for years or longer. What was our take on that? Well, we modified our anisotropic ratchet conveyors and made them flat, at least from an optical transparency point of view, that we simply made some regions that are more or less hydrophobic, but other than that, the surface is essentially flat. When my student initially proposed that to me, then I said, no, that's not going to work. You need the topography, you need the pillars and the physical roughness. But he went ahead anyway, and he came back a few days later, and well, I got it to work. This is what we want to do ultimately then, that you have particles sitting on the surface, and on the surface you have essentially a water air interface that is getting pulled along with this principle of the arc surface. And it's carrying along the contaminant. Now there's quite a bit of math, some modeling that you can do that I'm not going to go to in detail right now, but the ultimate effect is something like in this video that you're seeing here. This is a 10 microliter droplet, and it's carrying a few grains of sand. It turns out that you can actually load these drops with a lot of sand, up to 50 or more % in weight, and the effect is still working, so you can still move the drops along. Here's the experiment that I wanted to show you, and let's see. The video started with the first experiment already done, but I just let it run here. And what you see here is that the drops are following this invisible, this flat arc pattern that we created on the surface. It's transparent, it's essentially invisible, but the drop basically knows where to go. It follows this track and it picks up the dirt along the way. Within a few seconds here, within about 10 seconds, it has picked up all the dirt in this area, and well, now it's slowed down because it's loaded with all these contaminants, but it keeps moving along this, well, I shouldn't call it circular track, but it's a loop. Well, I guess here it goes again, but I'm just telling you a little bit more what we wanted to do with that. Well, there are several publications that have come out over the last couple of years, but what you're seeing here is one 10 microliter drop that cleans about, well, 1 square inch, about 5 centimeters square, and it does that in about 10 seconds. So if we do a simple extrapolation, then we can ask, well, how long does it take to do a 2 meter squared surface? Well, we wouldn't do that with one drop, but you could actually do that with 100 drops. So you multiply 10 microliters by 100, you get 1 milliliter. That would take about 40 seconds according to this calculation. So compare that with what's currently being done, where you need about 2 liters for cleaning of a solar panel of 2 meters squared. Now here with this principle, we could do this with about 1,000 times less water. One of the reasons why I believe this is working, because we have this very precise control of where the drop is actually moving. Now here's another experiment. So my student D, he put an actual solar panel, and he put this pattern onto the cover glass of the solar panel. And while he was cleaning it, while you see the drop moving back and forth, capturing some of the more and more of the particles, the solar panel essentially captures more and more of the light that is being exposed to. So he's measuring this at the same time. So you're going from about 70% of, well, the nominal efficiency to about 90%. Now it turns out that under the right conditions, when you pick the right materials for this arc track, then you can actually get even an improvement in efficiency, because you can do the refractive index matching that actually reduces reflection and increases the transmission. So the fact that there is a pattern on the cover glass is not necessarily a bad thing. It may actually improve the efficiency, just like any anti-reflective coating would do. So now you can do some characterization on that. I don't think I'll go into a lot of detail here, but we looked at sloped surfaces as well, because, well, if we have installations of solar panels, often they're at an angle, especially if you're living in more northern or, well, more southern hemisphere parts of the hemisphere. So it can also work on sloped surfaces, and depending on what kind of materials we use, we may or may not lose or even gain some of the efficiency in the transmittance. So far I've shown you this principle with vibrating surfaces. So you actually have to give it mechanical movement. And of course, that may not be an ideal solution for solar panels. You don't want to shake the entire system, even though actually it turns out that the frequencies that you need, so 40 to 60 hertz typically, often these are the kind of mechanical vibrations that you get in large installations. So for example, if you look at cars or at planes, the vibrations that you can observe usually peak around that area. So in this range of around 60 hertz. So you could possibly design a solar panel so that it naturally vibrates at those frequencies. But what if you don't like that? What if you don't want to have any kind of vibration in the system? Well, you can use electrowetting instead. So here's the principle for that. You would have embedded electrodes, and you're applying an electric field, and depending on the strength of the field, the drop will change its shape. And in the combination with this arc pattern, you can again make the drops move. So here's a simple demonstration on how this can be done. So we have some drops sitting here, and when you apply a voltage, then the drops are moving. And here we design the patterns in opposite directions. So some drops are moving towards us, some others are moving against us. And these voltages are usually in the single volt range or in the tens of volts. And now you can, as I already mentioned, you can do this on sloped surfaces as well. So hopefully in this video you can see a system with an inclined angle of about 30 degrees. You can see that each row carries one drop. And the idea was that once the drops are on the side, then they eventually collect, and then when they combine, they become too heavy to stick, and then they just fall off the panel. So that would be our cleaning principle in general, that we just let the dirty drops fall off the panel and then supply more drops for cleaning. So here in the lower video, a little bit more difficult to see, but we're depositing drops, and they're collecting here on the side of the solar panel, and eventually they'll fall off the system. And now, there are actually many other things that you can do with the system, and in the remaining time, where I have only a few minutes left, I want to show you a couple other ideas. So far I've shown you frequencies that are in the 40 to 60 hertz range typically. But you can actually also work with much higher frequencies. And then you get really into a regime of liquid dielectrophoresis. This may have some advantages, especially if you're worried about hydrolysis. So you don't want to break down your water drops into oxygen and hydrogen. Also use very high frequencies, but then you can just turn the voltage on and off. And this is what's happening in this particular video. And we actually had some conversations with Blue Origin, the company that's building a spacecraft, and they're very worried about their passengers who have beautiful large windows, but they're worried that the windows actually fog up, and they're looking for techniques on how to keep the windows from fogging up, because if you pay, I don't know, how much does it cost, $500,000 to spend 1 minute in space? You don't want to sit behind a foggy window. So how do you get the condensation off window? Well, here's one possible solution. So here's a drop that's moving along a surface, and you see some condensation on that surface that is being picked up by this drop that in this case moves with the DEP principle, even though we could have used the electrowetting principle or vibration as well. But in this case, we wanted to demonstrate the higher frequency control. And finally, the last principle that I wanted to show you that we've also been exploring was a surface acoustic wave. So in this case, we have a substrate that can create waves in, surface acoustic waves in the substrate itself. And at the same time, we have these arc patterns on top of them. So we combine the vibration again with these anisotropic or asymmetric patterns. And we can create them in different directions. So we can make the drops move, in this case, towards the center. So the goal here was to maybe combine 2 different drops, or here maybe 3 different drops that all follow different paths and then end up at the center. And in the video that you're seeing here, you see again the drop moving along the surface with the saw agitation. And here it's come, at this point, it's come to the end of the track. So here the drop is moving and then stopping and essentially waiting because the pattern has ended. And now, like in this here, I don't have a video for that. I just have some still images, but you can see that there are 2 different color drops that are moving towards the center again with the saw principle, and eventually they get merged between the orange and the blue drop. So this was actually described in a paper that just recently came out in Lab on Chip. So this was actually a slightly different direction for the research, where we were collaborating with colleagues in a local startup company that's working on microfluidic platforms. And in particular, they want to do sample preparation for mass spectrometry. So we combined our droplet transportation and droplet positioning with their techniques to do a droplet nebulization. So take a drop and turn it into a tiny droplets, many drops that then can be used in mass spectrometry. So here's an example of the drop that has already been transported to this particular site. Again, the arc track on which it has traveled is invisible here, but you can see the electrodes for the SAW device. And in the video, you see the nebulization process where the drop that was just peacefully sitting there in the center then suddenly turns into lots of tiny drops that are then processed in the mass spec instrument. So I thought this was maybe a good way to reach the end of my presentation here today. So essentially, ending it with a bang where we're blowing up things, and that's always fun to do that in an experiment where you see some exciting things happening at the small scale on our chips. And in this case, we could even see how many drops are being produced at different size scales. And you can see that the diameter sort of peak at about 1 to 2 micrometers. So I hope that this was interesting for everybody here with several different applications of droplet manipulation and in general with interactions and magic at the small scale on surfaces. I do want to maybe just make a few points to summarize my presentation here. Hopefully there's not too much text, but I mean, in general, I think we can still learn a lot from nature and apply the new kind of engineering systems. So in particular, we looked at the lotus leaf, but then modified and in a way improved the principle to actually have a system where we can very controllably manipulate small amounts of liquids. We applied that to self-cleaning of surfaces, but more generally to essentially a particular kind of lab on a chip platform where you can do a moving, sorting, mixing, merging, all on this very simple device that essentially just uses texture and either vibration from mechanical agitation or from an electrical field. The self-cleaning surfaces are still a work in progress, but we believe that we can make much more efficient or produce much more efficient ways of making solar panels clean, and also look at other applications, for example, cameras that are in hard to reach places that you would like to keep clean over long times. So lots of exciting things happening there right now, but there are also some challenges, and that's maybe something for the entire audience, and I'm very happy to collaborate with colleagues here. So what are the main challenges that are remaining? Well, I already mentioned that for solar panels, you always have to worry about durability. You have panels sitting in harsh environments, exposed to the sun, exposed to sandstorms, exposed to maybe birds that leave all sorts of things on a solar panel. How do you create these surfaces and make them durable for 10 or maybe more years? Especially hydrophobic, sticky materials, how can you get rid of them? Well, some ideas are on some catalytic materials that essentially break down the organic components into smaller particles that then can be carried away with the techniques that I've shown you. The final point that I wanted to make is, well, where does the water come from? Essentially, I would like to be completely independent. I do not want to have somebody going there with water buckets and refilling some tanks. And we believe that we can capture enough water from condensation. And even if you look at extremely dry environments where during daytime the humidity drops to 10 or 20%, at night, actually, the relative humidity still goes up to more than 50%. And that is enough we believe, to capture the water from the air. And at least for the small volumes that we need, we can then resupply our cleaning mechanism. So that's something that in principle we believe we can do. And nature again has shown some examples for that. There are some desert lizards that can capture moisture from the air, or maybe even extract it from the sand on which they walk. So I would like to build something like that and make a completely autonomous self-cleaning solar panel. So with that, I want to thank the entire audience for attending today. And many people have contributed to that. I already highlighted Deason. I want to do that one more time. We've done a lot of exciting work here. We're also working with NREL on experiments with our solar panels. And of course, there was support from many different sources that I'm acknowledging here on this page. But I'll leave it at that. I think we have some time for questions. So again, thank you very much for your attention, and I'm looking forward to continuing discussion on this topic. Thank you.
Thank you so much. Let me put my screen up here. Well, thanks so much for sharing both your beautiful data and also your vision. We have quite a few questions from the audience. We'll start with this one. For the texture on the surface, instead of pillar arrays, have you tried mushrooms or other shapes? I think you mentioned some other people's work along those lines. And also, what can you say about the surface energies of different shapes?
So the first part of the question, have we tried other kinds of shapes? In our lab, we haven't. We definitely thought about that. And yeah, I mentioned earlier the work by C.J. Kim, just as one example, who built these beautiful mushroom or umbrella shapes with double re-entrant features. So I believe that this may be necessary to go to really the next step if you want to deal with a larger range of materials that are more sticky. The surfaces that we've created are very simple to make. We can mold them out of one master. So there's a trade-off in how far do you want to push this, how much is necessary. So ultimately it comes down to cost. And I think often when you talk to solar panel manufacturers, then they look at tiny fractions of dollars or maybe even cents on what is efficient. So definitely like to do that, whether it's for solar panels or maybe for more high value per area applications, like some cameras where just a few millimeters may actually, square millimeters may make a difference. Now, what can I say about the surface energies of the different shapes? Well, there's a lot of literature out there, and the Cassie-Baxter equation is, I believe, dating back to the 40s, and there were several improvements or modifications in the meantime. But still, this model is, I think, very useful for many of the practical applications. Again, these mushroom shapes give you the most extreme situation where you can get essentially drops that are overhanging and really get close to 180 degrees of contact or apparent contact angle. This is something that we cannot do with just the regular rectangular shapes. But I think this is very well understood and well documented in the literature. So you can really design your surface up to the degree, up to the level that you need. Happy to explore that more in the future when we go into the next generation of our devices.
Very nice. Next question. For the Ratchet design, how far can it drive droplets? And can it drive objects other than droplets, for example, living cells?
Yeah, so I think the first part of the question is very easy. So the Ratchets don't have a limit, and that is really fundamental difference compared to the gradients, where you always have a high energy state and a low energy state, and you always end up in the energy minimum. For the ratchet, you don't have that. So you can make paths that are in principle infinitely long. We can also make circular paths. I showed you the one experiment where you have a zigzag pattern that eventually loops back, and you can make that arbitrarily large. Of course, if we talk about surface cleaning, then eventually the drop gets loaded up with more and more contaminants, and that will then change the behavior of the drop eventually. So that's a more, well, practical limitation of how long the track would be. Another question actually that sometimes comes up in this context is the question about evaporation. So how long do these drops actually stay, and how quickly do they evaporate? And one of my students did some experiments on that. He had a circular path and just let the drop move in circles. And he sat there for about half an hour and occasionally had to change the frequency because the drop lost some of its volume. But the kinds of drops that are shown you with a few microliters in volume, they survive for at least tens of minutes or maybe even for hours, depending on the relative humidity in the environment. Now, can you move other things? We've always thought of this as essentially as a lab in a drop, if you want to talk about living cells. So we always thought as the drop of water as the container. If we just put a cell on the surface, we've actually never tried that, so I don't really know. But what's really essential to this system is that you have a substantially hydrophobic surface, and that you also have a contrast between different regions. So with each one of these arc patterns, you see a contrast in which the contact line then can move along. If you have a cell sitting there, that may not be the case. You may not get enough of a sort of hydrophobic effect to make that work. So my choice would be to transport everything that I want to move along inside the drop. As long as it's an aqueous solution, as long as there is enough water, it should work.
Great. Third question. For the fabrication of the texture gradient, how is the uniformity of the spin-coated film on the silicon microstructure? Will those hydrophobic microstructures make it hard to be spin-coated? I guess the question is it hard to do the spin coating, and how uniform are the films that are created?
Yeah, that's a good question. There are actually many different ways in how you can make these surfaces. And the first version that I showed you was a silicon wafer that was then coated with essentially a spin-on Teflon. There are definitely some concerns if you work on rough surfaces. It turned out that these are very thin films, so they're naturally creating just a very thin layer, even on textured surfaces. So the kind of shadowing or streaks that you sometimes get doing spin coating, we didn't really observe that on these wafers. So there was a quite a very reliable coating. Now we had other coatings where this is not really an issue at all. I didn't specifically mention it today, but you can also do vapor coating. So the FOTS and TMS, so these are silane coatings that are deposited in the vapor phase, and there, in the extreme case, you get a self-assembled monolayer that coats, well, whatever pattern you have on the surface, and the topography doesn't really matter in that case. So you get very reliable, very uniform, and ideally just a single molecular layer thick coating of the surface. So, and I think overall, even if there were some variation in the thickness, for example, in the spin coating, I don't think it would really matter much, because what really only matters is the actual surface property. So as long as you get the contrast, whether it's due to topography or due to just a patterning between different degrees of hydrophobicity, that is really all that matters. I think the slight variations in the thickness would not change the behavior of the system.
Mhm. And our fourth question. Thank you, Professor. There are many efforts on self-cleaning solar panels, micro, nano textured structures and coatings. Did any of these approaches yet make it into commercialization in solar cell factories?
Yeah, this is again a great question, and it is something that we've been talking about a lot. Actually, my student Dee, that I mentioned on various occasions, was very entrepreneurial, and we went out, made pitches to various occasions, and he actually also won some awards for his entrepreneurship efforts. But at the same time, it is very tough to convince the industry to go in that direction. There are other kinds of solutions, again, with very hydrophobic materials. The big question is always, well, A, what is the added cost? And B, what is the durability? So I think for both cases, you need to make a very strong case. Now, as far as I know, there are some products in the market that actually have coatings. They're not patterned in this case. They're just simple coatings that reduce the stickiness and also reduce the reflection, so anti-reflective coatings. But the big question is, do they last, or do you have to maybe renew them every year? And then what is the cost related to that? So what I would like to have, and I think where we're still struggling, is finding just the right material that is transparent in a adequate way, and durable, even if it's exposed to sand storms and to obviously to sun during many years of operation. So I think we're just at the beginning for that, and as better materials come along, better ideas, we'll see more of these products. At the moment, they're really more of a niche.
Mm-hmm. Very good. And our final question, most of the materials in your research are silicon-based. What can you say about other materials?
Yeah, that's a great question too. And I think we're, as somebody who has been working in MEMS and microfabrication for many years, I'm just a little bit biased towards silicon. And I have to remind myself often that silicon is great, but it is not everything. And this, of course, is one particular example where you have to be on the lookout for other options. So the initial experiments were done on silicon just because it was the easiest way for us to build it. But later in some of the examples, of course, you saw we worked on glass substrates. We modified the glass surface with our ARC patterns. We also explored polymers. We had some nice results with molded PDMS materials that were stretchable, and you could show that you could bend the patterns, and the droplets would still follow the tracks, even uphill, downhill. So there are definitely many material choices out there that you would just want to adjust for the particular application. But I think when we're talking about solar panels and we're talking about the standards in the industry right now, then we have to look at glass and how to modify the glass surfaces to get these properties in an efficient and durable way.
Very nice. Well, thank you so much. This is the point where we'd be able to come together across the stage and shake hands and hand over a plaque. But as for our earlier lecture, for now, all we're able to do is thank you from a global audience for sharing this very beautiful work. Look forward to a time when I can see you in person along with the other panelists that we had, and Jillian Buriak. Thanks for really a terrific lecture. We appreciate you getting up very early and sharing your work with the world.
Yeah, thank you very much.
I'll point out that we have an interesting set of lectures coming up the rest of this month, including the Mine Young Scientists and ACS Nano Rising Star lectures. I want to thank Alice Zhang at Beida again for putting this series together, and Chuanjun Zhao for helping at my end this morning and each time that I've hosted. We have a growing family of presenters, and now for those of you who celebrate, we'll let you get back to the Mid-Autumn Festival. Enjoy it, and we'll look forward to seeing you next week and the subsequent Fridays. Thank you all so much.
Thank you.